In this video I'm going to go through DC electricity, which is part of Unit 2, and I'm going to go through ISP task 3. The reason why I'm not going, ISP task 2, I apologise for that. The reason why I'm not going to go through 1 is because that's a review task, reviewing the work you've done in Unit 1, and ISP task 2 is related to the work you're doing in Unit 2, so it's the first ISP task of DC electricity Unit 2. So you can see the specification points that are being covered and the page references to look at if you're struggling, and the key concepts that are going to be covered are current, potential difference, resistance and resistivity, using the equations for Q, V, I, R and resistivity, and being able to find the resistivity of material using a graph. Now remember, this is one of these sort of core practical ideas, the ideas of using resistivity, find the resistivity from a graph, the idea that there's resistance against length, and then from the gradient of that graph you can find resistivity. That's one of the things we need to cover. So let's get stuck straight into explaining everything in one, which is pretty straightforward. There we go. Right, so the first thing I want us to do is describe how to find the resistivity of material using a R versus L graph. Include the unit for gradient of this graph. Okay, so we need to use the ideas of y equals mx plus c, the gradient, micrometer, using the idea of micrometer, cross-sectional area, resistance, length, and ohms. Okay, so if I so I'm just waiting for my webcam to focus. There we go. Right. So for the idea of a graph of R against L, which is the first thing we'll draw, we know that for a wire they're directly proportional, and the gradient is the key value that we need to find from this graph. We know we're looking for a change in Y over a change in X. So we need to figure out how this is linked to an equation. So the first equation, so we know the equation for resistivity is that resistance is equal to resistivity times length over cross-sectional area. We know that the cross-sectional area comes from pi r squared. There we go, sorry. And we know the r comes from the diameter, and the diameter comes from micrometer. So remember, micrometers measure to tenths or hundredths of a millimeter, so they don't go all the way down to a micrometer in terms of the value, but they can measure tenths of micrometers in terms of the value that you can measure to. So how from this graph are we going to get resistivity? Well, this is ohms on this axis over here, this is measured in meters. The gradient of this graph is therefore going to be ohm over meters, so it's going to be ohm per meter. Now that's not the unit of resistivity. We know that resistivity has the unit of ohm meters, so somehow we're going to need to do that, and it's clearly by multiplying by m squared. So we're going to have to multiply the gradient by we're going to need to multiply the gradient by m squared, so that's the area, and we're aware of that. But we need to prove it. We need to prove it not just by units but by the equation. So we know it's a straight line through the origin. Okay, so we need to prove that with this equation here. So by doing y equals mx plus c, r is on our y-axis, L is on our x-axis. Okay, so that leaves no plus c. That means rho over a is our m. Rho over a is our m. So r is lx. So r is y, L is x, and m is therefore rho of a. Remember, it's rho, not p. Okay, so that's the first part of explaining everything in one done, clearly showing how to find from the graph the resistivity. So resistivity is going to be a gradient, or m, times by our cross-sectional area. Straightforward as that. Second part, okay, so we've got we've got to draw a current voltage graph, current voltage graph for a diode, or voltage current graph for a diode, a filament lamp, and a resistor. Explain the shape of these graphs. Would I explain the shape of it? This is something we should have covered. You should have covered from GCSE and should know quite well from GCSE. So there's 3 graphs. Let's draw our axes in there. So remember, there's 4 quadrants, positive and negative on both. Okay, let's put current on our y, voltage on our x, potential difference, sorry, on our x. Right, so let's draw the shape of these. We've got one that's like that, we've got another that's like that, and then we've got another that's like this. Okay, so it's probably a bit further along actually before it curves up. Okay, so that's our filament lamp, that's our resistor, our ohmic conductor, and this is our diode. Okay. So remember, diodes have that little triangle with a line in it. Okay, shows direction of current flow. So diodes only allow current in one direction, only allow I to flow one way. So the explanation for that is that they have a high resistance in the other direction. So if the current can flow that way, in that direction you're going to have a very high resistance. That's almost infinite in terms of the resistance. So high resistance this direction, so current can only flow that way. In terms of the resistor, okay, so in this situation over here, V is directly proportional to I at constant temp. So you have to state at constant temperature. That's a law, that's Ohm's law. Okay, so this obeys Ohm's law because V is proportional to I at constant temperature. Okay, so that's resistor obeying Ohm's law. Filament lamp. Okay, so you can see for part of it, it does actually obey Ohm's law, but then at high current in either direction, so high positive or high negative current, it curves off, and we need to understand what's actually happening. Whereas, as there's a higher potential difference, there's a larger current flowing, and as the larger current flows, the wire gets hotter. As the wire gets hotter, the resistance to the wire actually increases, and as the resistance increases, the current can't increase as much. So that's why it levels off, it almost plateaus. So that plateau comes about because of the fact that resistance is increasing with increasing current because of the fact that the higher current leads to higher temperature. We're fully aware of the fact that normally higher resistance means lower current, so surely if the current is higher then the resistance must be lower, but what's actually happening is that at high current the temperature gets very hot and it stops the current from being able to increase. So that's why that happens. You need to be able to you need to be able to explain that idea. So the fact is that as voltage increases, current increases, okay, temperature increases, therefore resistance increases, so current levels off. Okay, that's your idea, that's your thought process to that. Excellent, so that's the explaining everything tasks done. We might as well jump straight into the questions, which are further down. Okay, so let's get straight into these. So remember, I'll jump to the mark scheme where I can, rather than have to write everything out, unless there's a detailed calculation that needs to take place. Okay, so the first one is just a question sheet. Question where you have to put in the correct word for each of these. So you need to select a word from each match's description, and each word can be used more than once. So quantity, so these are all quantities, not units. A quantity that can be measured in joules per coulomb. So a joule per coulomb. Okay, so we're after work done over charge. Okay, work done over charge. So you look to your equation list and look for the one that's got work done over charge. Look at electricity work done over charge, straight away potential difference. Okay, so let's make that nice and easy. First one's potential difference. A quantity that equals the product of two other quantities in the list. So a product means multiplication. So I multiply two things on there, gives you something else. Well, if we're looking at current, you know that current is equal to charge times time. Time's not on that list, so that's not usable. If you want to know where I got that equation from, it's just a rearrangement of that. If we look at the other equations that we've got here, we've got R is equal to V over I, so resistance, potential difference and current. So resistance, potential difference and current are all on here. Current times resistance equals potential difference, that one's also PD. So that just comes from the rearrangement of V equals, so R is equal to V over I. If we rearrange that, we know V equals IR, so therefore potential difference is the product of two others on the list, i.e. current and resistance. A quantity which equals a rate of change of another quantity on the list. Okay, so as we know, current is a rate of flow of charge, so it's a rate of change, therefore, of charge, so that must be current. So far we want potential difference, current. A base quantity in the system, okay, so we know that current is a base unit, so amps is a base unit, therefore current is a base quantity. A nice question to start us off, to warm us up, to remind us of the key facts we need to know about electricity. Okay, let's move further down. And get on to question 2. Right, a multiple choice question, just like the bit above essentially. So how much electrical energy is required to move 4 millicoulombs of charge with a potential difference of 36 volts? So, okay, it's a similar idea to what we had before, similar equation, it's just that one there, also same equation, it's just that one there. So we've got 4 millicoulombs, so that's equal to 4 times 10 to the 3 coulombs. Remember, it's a bugbear of mine where people are trying to divide this by 1,000 and make a silly mistake in the number of zeros. The reason why scientists use the idea of milli is so that we can use standard form straight away. Standard form makes life a lot easier. I know it's not standard form that you're used to, because sometimes it can be 40 times 10 to the minus 3, okay? But scientific standard form in this sense makes things very, very straightforward. So there's our charge. We've got charge, energy divided by charge. So therefore, if we want the energy, we need to do voltage times by charge. So we're multiplying this 4 times 10 to the minus 3, okay, by our 36. Okay, so we know that this number over here is going to be close to 12. Sorry, 120 in front, so 120 times 10 to the minus 3, somewhere in that sort of region. Okay, so we're looking at potentially B here. Let's just double check that though. Let's get the calculator up. 4 times 10 to the minus 3 times by 36. Okay, so there we go, straight away B. Okay, so note how I predicted what the answer would be, and therefore, and then confirmed it using the calculator, making doubly sure that I'm getting the correct answer. Okay. State the word equation that is used to define charge. Okay, so charge is essentially going to be current divided by time. So if we look at current times time. So if we look at our equation from above, if you rearrange that for charge, it's current times by time. Okay, so charge is the amount of current that flows in a set amount of time. Define potential difference, we've already done that once already, that's the energy per unit charge or joules per coulomb, either of those is fine. Okay, so we've done the first 3 questions, let's just double check those, check that we've got them right. So, first 3 questions. First one, okay, so potential difference, current, just like we said. B, charge is current times time, and work done per unit charge, and it's as straightforward as that. Right, next. Here we go. Right, okay, so we've got, I haven't finished question 3. So, we've got a power source here with the light bulb. Now, to calculate the energy transferred when 20 coulombs flow through it, we know it's connected to a 9-volt battery. Sorry about that, going over from one page to another. So that's 9 volts. Okay, we've got 20 coulombs, large charge. Okay, so you want to figure out the energy. Okay, so energy is voltage times by charge. Okay, so that's potential difference times by charge. So rearrangement of the equation from above. Okay, so that's going to be 9 times by 20. This could be 180. Okay, so let's confirm that one. So we've got everything up to 3 marked up. Okay, so please do mark these as you go through them so you can double check. And if you are getting stuck, and if this video isn't helping, use a mark scheme. But in future, try to use a mark scheme before coming straight to the video, because you never know, you might be getting them all right and you need to build your confidence in answering these questions. Question number 4. Okay. So Io is one of Jupiter's moons. Some of the electrons released from the volcanic surface of Io have an average velocity of 2.9 times 10 to the 7. Well, that's nearly a tenth of the speed of light. That's very fast. Towards Jupiter, so they're going towards Jupiter. That's probably going to be key. The fact that I've noted that in there. So they've given us a distance between Jupiter and Io. So that's 4.2 times 10 to the 5. Show the time taken for these electrons to reach Jupiter is about 14 seconds. Okay, right. So we've got a velocity. We've got a distance, we know how to get time from that. Oh, hold on, this is unit 1 surely. But remember, there are synoptic elements where they tie together unit 1 and unit 2 together. This is a straightforward question, so it's completely okay to ask this question in unit 2, even though it sort of touches on unit 1 content. Okay, so speed or velocity is equal to distance over time. Okay, therefore time is equal to distance over velocity. So we've got 4.2 times 10. Sorry, I haven't got the calculator in front of it. So 4.2. Let's clear this all so you can see it clear. 4.2 times 10 to. Now watch this carefully. Okay, it's times 10 to the 15 kilometers. We need to convert that into meters. So instead of being times 10 to the 5, it's going to be times 10 to the 8. Okay, That's our distance, and our velocity is going to be 2.9 times 10 to the 7. Okay, so there we go, we end up with our 14, rounds to 14. Okay, that's great, nice question. B. So now we know the current is 3 times 10 to 6 amps. Calculate the number of electrons that arrive at Jupiter per second. So we've got the current. We know that current is equal to charge times by time. Okay, so we can use that idea. But that's not going to tell us the number of electrons that are actually arriving. That's just going to tell us the charge that actually arrives. Okay, but if we know the charge, we know the charge of one electron from our data sheet, so we can divide one by the other. So we divide our overall charge by the number of electrons, okay, and then therefore figure out how many electrons actually arrived. So let's have a look at the mark scheme so I can guide you through this. Okay, remember we do use the mark scheme to help us so we can see how we can lay things out, and also to clarify our thinking. Okay, so Q equals IT, we know that. Ignore the N for now, ignore this NE for now. Q is equal to I, so you can, actually, by the way, we can just quickly check, we got the last one right as well. So Q is equal to IT. So if you figured out the charge, so I times by T, and you divided that by the charge of one electron, 1.6 times 10 to the minus 19, you would figure out the number of electrons that actually arrive. Now, that's a huge number, and that's about right. We should have a huge number of electrons actually arriving. Okay, it's a straightforward process. So the idea, if you want me to show you how to guide you through it, first thing you need to do is to take your current and your time and multiply them to figure out the charge. Then you divide the charge by the charge of one electron, 1.6 times. So you take this charge, divide it by 1.6 times 10 to the minus 19, and that tells you the number of electrons you actually had. It's a nice question to get. A lot of people will miss the trick with that question, but it's quite easy to spot if you've got a good understanding of the stuff that we're covering. Right, nearly there. Here we go. Right, state the direction of current. Okay, so we know that current is a flow of electrons, so technically it should be going from the direction of negative to positive. However, we are fully aware that conventional current goes from positive to negative, so it's always going to be from positive to negative. Okay, so from positive to negative, that's the way it actually flows. But it actually is saying right now that some of the electrons have been released from the volcanic surface of Io and have an average velocity towards Jupiter. So the electrons are going towards Jupiter. That must mean the current must be going away from Jupiter, from Jupiter to Io. There you go. Okay, so away from Jupiter to Io. Excellent. Okay, so let's get question 5 up now, so we can work through that. Okay, so we've got a series circuit with a parallel circuit, sorry, with 2 resistors in parallel, but if we combine them, we can make this into a series circuit. Calculate the potential difference with a 15 ohm resistor. Nice, straightforward. Okay, remember potential difference is equal to current times resistance. There's no internal resistance in this, so we don't take that into account. So resistance times by current, okay, that's 3.6. So what I would do, is if you have this in front of you right now, is write your 3.6 down here, but also write it over here right next to this resistor so we know. Now remember, if this is getting 3.6, this must be getting 3.6, okay? And so this whole combination here is getting 3.6, so that must mean 2.4 is going over here. So calculate current I through the 4 ohm resistor. Okay, so we want to know what's going through the 4 ohm resistor. So this is slightly trickier. Okay, so there's a few ways to approach this. The first way is the way I was just discussing then. You know the resistance. I've just told you how to figure out the voltage. If this is 3.6 added together, that must be 2.4 because they need to add up to 6. Or what you could do is you could figure out the resistance. Actually, no, you can't do that yet. We don't know this resistor, so you can't figure out the value of this resistance combination yet. So the only way to do it is to know that this is for 2.4 volts, okay, and the resistance is 4 ohms, so you need to figure out the current. So V is equal to IR, as we stated before. V is equal to IR, so I must be V over R. So that's going to be 2.4 divided by 4. Okay, which gives us 0.6. There's 0.6 coming through here, so make sure you write 0.6 coming through here. Straight away, knowing our circuit rules, if 0.6 comes down here, 0.24 comes down here, the rest must go up here. Okay, so that's 0.36 must go in this direction up here. 0.36 must go up there through R. Okay, so calculate I2, just done that. Okay, remember if 0.6 comes in, 2.4 goes this way, 0.36 must go up here. And the resistance R, well, if 0.36 is going through here, if I2 is 0.36, and we know the voltage is the same as before, okay, so I'm trying to remember what the voltage of that was because I haven't written it on, as you guys will have. It's 3.6 is what it is. So if that's 3.6, that's 0.36, we can figure out the value of R. So R is equal to V over I, so that's 3.6 divided by 0.36, which of course gives us 10, so that's 10 ohms, okay, so C would be 10 ohms. Let's double check we've got all those right. Okay, so we blitzed our way through that question pretty quickly. So play it back, please, if you didn't catch everything I said. But let's double check this. 3.6 volts. That's the first part of it. 0.6. That's the second part. It has 3 marks attached to that. That's a lot of marks for a pretty straightforward idea. And again, 3 marks attached to that 10 ohm calculation for a pretty straightforward idea. 7-mark question. I'll probably reckon about 3 minutes for those of you that have got a good grasp of this. This is certainly a question I do time and time again to make sure you understand it, to make sure you can access it quite quickly. It's a good question to get. Right. So next bit, question 6. Okay, so this is a practical that you've all done in class. Okay, finding the resistivity of wire. So it's mentioned in the explaining everything. So we need to show that the cross-sectional area of this wire is 2 times 10 to the minus 7 meters squared. You have the diameter. If you go from diameter to cross-sectional area, you've already got that. Remember how to do it, work back through it. Diameter halved is radius. Radius squared times by pi is cross-sectional area. As straightforward as that. Okay, so we'll just quickly do that in the calculator. The biggest mistake that people make is not converting into meters. So 0.5, don't make it tricky for yourself. Times 10 to the minus 3, sorry, I've just put that, I should put it in there. Don't make it tricky for yourself. 0.5 exp minus 3. Just keep it in scientific standard form and then square it. Okay, then you're going to multiply that by pi. Okay, and my answer is incorrect because the fact is multiplied it incorrectly. Let's do this again. 0.5 exp minus 3. Let's close the bracket off. I bet it's going to moan at me about brackets. Your calculators are nice and new, so they won't do that. This one will. Oh no, it's going right so far. I need to multiply that by pi. Interesting. Show that the cross-sectional area of this wire is... Of course, what I'm not doing is halving my diameter once I put it in there. Shows even the best of us make mistakes. Right, okay. I'm not saying that I'm the best of us, but there we go. Squared is equal to that, multiplied by pi. Okay, so there you go, 2 times 10 to the minus 7. See, the key thing there is spotting your mistake and not just leaving it. Okay. Right, next. Says the highly embarrassed teacher. We've got a table, so you're definitely going to ask you to figure out that final column. So it says complete the third column and use the data to plot a graph of resistance against length divided by area. So all of these are just the length divided by the area. All of these over here, sorry, are just the length divided by the area you've just done. Look carefully, they want it plotted times 10 to the 6. Okay, so whatever value you get, you've got to keep it to that scale, whatever it is, times 10 to the 6. Okay. So you know what this graph should look like. It should be a straight line through the origin, okay, and that then gets plotted on these axes here. And again, with the idea of 10 to the 6. It's asking you to draw a line of best fit and calculate the resistivity. Well, this time we've got R against L over A. So you've got a straight line for that. And this time the gradients could be something different. Let's have a look. So let's write our equation out. There's our Y. There's our x. So m this time is just the resistivity. It's not resistivity of area this time, therefore the gradient of this graph tells you the resistivity. It says suggest an explanation for the anomalous results obtained in this experiment. So there were some anomalous results and you plotted this. Remember, there's many potential reasons for this. There's error when reading the resistance, small fluctuations of resistance, incorrect incorrect measurements of length, random errors potentially even, so any of those would get you the marks. Let's have a look and see what the mark scheme says. Okay, so there's the, you can check your you can check, just to actually, first thing to point out is just to show you, I would have still got one of the marks because I used the correct expression. I just forgot to half it, so I still would have got one of the 2 marks. That ain't that bad. So next bit is about just filling in the results there, so you can check your results against those. Okay, so you can see already from that anomalies it should be going up in 0.5. And they're not really anomalies, they're only ever so slightly off. Okay. So again, resistivity calculation is a straight line drawn from the origin, large triangle, so it's just find the gradient, remember. So ideas is higher current or lower resistance for shorter length. Okay, so remember, when a short length you get a high current, that will affect the resistance. We've spoken about that in class. Non-uniform area or diameter, so we've spoken about that as well. And contact resistance, we've also spoken about. Sensitivity of meters, that's what I was talking about in terms of the fluctuations. So any of these ideas would have got you the mark. Any of those would have got you the 2 marks available. Right, now it does say task 3 next, however I haven't put task 3 on any of the ISP tasks, so I'm going to quickly whip through these questions as well to make sure you understand these. So I would do these when you do task 2. These questions, although it says task 3, when you do task 2 questions, I'll do these as well. So the content is the same essentially. Name the component, that's a diode, very clearly, straight off the bat. Calculate the resistance when the potential difference is 0.6 ohms, 0.6 volts, sorry. So you go up from 0.6. So I'm sorry it doesn't look particularly clear on the printout, and then go across for the current, so it's about 100 milliamps. So you just do your 0.6 volts divided by 100 milliamps. Remember, convert the milliamps into amps. State what the resistance is at minus 0.8. Okay, so remember it's infinite or very high. And a practical use for this component, we know this question gets asked very, very often. Converting AC into DC, used to emit light and LED, any of those are correct. Right. So this shows a current potential graph for this circuit is used to make a current potential difference graph for a 12 volt 24 watt filament lamp. Calculate the current in the filament lamp when the potential difference across it is 12 volts. Right, so they want the current when the potential difference is 12 volts. So we know from our equation list, so feel free to go up and quickly have a look at it if you need to, but power, just wait for my webcam to focus again, there we go. Power is equal to current times by voltage. They want current, so that's power divided by voltage. Okay, so that's going to be 24 divided by 12, 24 watts divided by 12 volts, which is 2 amps. So nice, easy 2-mark question to get us warmed up. Sketch a graph potential difference for a filament lamp. Right, we know that. It was an explaining everything. That's why we do these tasks. Make sure you label your axes. I would actually flatten these off a bit more. Don't do what I've just done and have it curl back on itself like that. Incorrect. Would not get the mark. Make sure it is flat. Don't let it curl back on itself. That's much better. Oh, I haven't labelled the axes. Right way around as well. Current is the bit that levels off. That's the way to remember that. Current levels off, voltage doesn't. Voltage can continue to increase. So explain with reference to the filament the shape of your graph as a potential difference across the filament increase from 0 volts to 12 volts. I've already spoken about that at the start. Okay, got it on the sheet over here for my wonderful graph that I drew over here. Okay, so you've got the idea that voltage increases, current increases, temperature increases, resistance increases, which means the current can't increase anymore and therefore levels off. Now, you might not have covered this work yet. If you haven't, then don't do it, but if you have, then please do have a go at it. If you haven't, actually, you can still look it up and do it. It's not particularly difficult. Okay, so it's talking about the idea of I equals NAQV. Okay, so that's the drift velocity equation where N is the number of charge carriers, okay, and V is the drift velocity of the charge carriers. Okay, and then talk about a metal conductor and a plastic insulator of the same dimensions. They're applying potential difference across each. Explain how the relative values of N for a metal conductor and plastic insulator affect the current in each. So metals have high values of N, plastics have low values of N. High values of N means high current, low values of N means low current. Now we've got a student with 2 pieces of copper wire. Okay, they're called A and B, and they're in series with each other. Draw this out. Please make sure you draw this out to get your head completely around it. Don't fall foul of not drawing this one out and therefore not getting and losing a mark. Okay, so A and B. Let's finish off the rest of it first. It says the diameter of A is twice that of B. So A is going to be twice as thick. There we go. Right. So that's A and that's B. Okay, and it says they're in series. with each other and a battery. Right, okay, so let's get this battery in here. Okay, they're in series. Straight away in series, we know the current is going to be the same. So I is the same. Remember that, okay? Remember that. Calculate the ratio of drift velocity in YA to drift velocity in YB. Explain your answer, okay? So if the current flowing through each is the same, the only thing that can vary is, getting back to the equation, NVA. Okay, the only thing that's actually varied is a cross-sectional area. So that's gonna that can't affect the current. Okay, those two can't actually affect each other. So the only thing that's going to change is the drift velocity. That's a constant. That's a constant. So the only thing that can actually change is drift velocity. So let's rearrange for V. So V is equal to I N V over. Oh God, I'll just put a Q in there. Oh, I do want to put a Q in there. N Q A. I said V, I meant Q. So I N Q A. Okay, that's what we've got. A can be expanded out in terms of diameter. Okay, so that ends up being. Let's write this out correctly. I is equal to N Q pi divided 2 squared. Okay, so if my diameter doubles, my drift velocity quarters. Remember, it quarters because the fact is a square. Okay, so if my diameter doubles, my drift velocity quarters. That's the idea that we're actually after. So that's how you'd lay that out. You'd lay out the equation and then you'd state the fact that we just stated. So let's see what they're actually after. So let's quickly go through the ones we've been through already, the ones we've done already. Diode or LED is fine. I don't like stating LED. It's not necessarily an LED. It's definitely a diode though. R is equal to V over I. Again, calculating the idea of 7 to going through the idea. Remember to convert into the milliamps into amps there. Saying it's infinite or very high. Okay, we'll get you the mark. It does say the infinity symbol, but I would actually write infinity or very high. So rectification, AC to DC, or that sort of idea. Okay, named use or LED, any of those is fine. P equals IV as we stated before, 2 amps, just like we did. Drawing that graph with the curve off. Okay, so showing fair rotational symmetry. So you've got to show rotational symmetry. This mark scheme doesn't actually show that, although it should be. So here's the idea: as voltage increases, current increases, temperature increases, increase in resistance. So a small increase at I or the rate of I decreases, just like we said. 4 really nice marks. Okay. N and V as we went through charge carrier density, as I said, or number of charge carriers per unit volume. Either of those is fine. So like I said, N in conductors is greater, N in insulators is less, so larger current flow in a conductor, straightforward as that. It's dependent on getting that first mark though. Okay, so if you didn't get that, you won't get the other one. So there we go. Okay, so the same current in N and Q, so I've written that over here. The same, I is the same in both of those, okay, because it's in series. VB is going to be greater than VI, yep, we know that because the diameter's smaller, so you're saying if the diameter, because the diameter is smaller, so therefore the V's can be larger. Because as we were saying, if the diameter is so hold on, let me write it above so we can see it's clearly. VB is greater than VA. So if the diameter is doubled, the velocity quarters. Okay, so that's the idea. Okay, so I've got that idea over here. The fact that VB over VA is a quarter. Okay, so if the diameter doubles, it quarters. Straightforward as that. So you don't need to write it as a ratio, you can write it as a relationship as was stated there. Brilliant. So that sums through the whole of task 2 on DC electricity. So remember, mark up what you've got, go fill in the gaps after watching this video, write it on the front sheet so you can see what you're getting right and what you're getting wrong. Okay, thank you very much.